In this question, you're given an equation, a scientific equation that is a rate equation for the concentration in a chemical reaction, and how its rate of change with respect to time is related to the concentration itself. And you're given this equation, dc dt is equal to k times c squared. And in the first couple of questions, I ask you about, well, how is this equation linearized? So if we were to linearize this equation, you find out in part A that all it takes to linearize this equation is to take the log on both sides. When I take the log on the left-hand side, I just get the log of the rate of change. When I take the log on the right-hand side, let's do that in a couple of quick steps here. If I'm going to break apart this log using the properties of logarithms on the right-hand side, how am I going to break apart this log? I've got two things happening, multiplication as well as a power. If I'm going to break this log apart, what am I going to look at first? Yeah, let's separate across multiplication first. Again, when you're simplifying and solving, we tend to use the order of operations backwards, because what's being squared here is just the c. We have to deal with the squared after we separate the c from the k. So first we'll separate, and when you separate across multiplication inside of a log, what does it become on the outside of the logs? Addition. Thank you. Multiplication on the inside is addition on the outside. So we get the log of k plus the log of c squared. And now, how do we handle the power, c squared? Put it in front, bring it down. Right, powers inside of a log become multiplication on the outside of the log. And so I get 2 log c instead of log c squared. By the way, mathematicians, there's a bit of a domain problem with that statement. Because, for example, log of c squared is well defined when c is negative, but 2 times the log of c is not well defined when c is negative. Just food for thought for the mathematicians in the group. But for us, we'll be fine with this because our concentrations are always positive numbers. And so our linearized equation, this was the point of questions A and B of this problem, reads log of dc dt is equal to log of k plus twice the log of c. Tell me, what is the, if we think of this as a linearized equation in the linear variables y equals log dc dt and x equals log of c, then where is the slope? Yeah, the slope of this linear equation is right there. It's 2. And how about the intercept? Intercept is the log of k. Right there. Which means if I'm in the laboratory and I want to know what value k has, and I collect some data, then the value that I'm going to get for k in the laboratory is going to come not from the slope on my graph, but more likely from the intercept on my graph. And that was the point of part B. But now, the part you've all been waiting for, part C. In part C, the question is, given this equation, dc dt equals kc squared, then what units must k have? So group that worked on 4, how did you determine in this problem what were the units of k?
We just plugged in what we already know for the other units into the equation.
Right, so you know the units of everything else in this equation. The units of C were moles per liter. And what were the units of dc dt? The rate of change, the time rate of change of concentration. Where'd you get those units? Moles per liters per second, and how come? Very good. Yep. Again, this is a derivative. It's a rate of change. It's a slope. And so its units are the units of the top quantity divided by the units of the bottom quantity. Top quantity is concentration in moles per liter. Bottom quantity is time, measured in seconds. And so dc dt is moles per liter per second, which I think you guys rewrote, you ladies rather, rewrote as moles per liter times seconds. Just ship that L into the denominator. And so then you end up with what you had, right? That you've got this equation which has moles per liter seconds on the left-hand side, and then on the right-hand side, that C, which has units of moles per liter, is getting squared. So just to make this as readable as possible here, not because of your handwriting, just because of the camera that I used here. Makes it kind of hard. You've got moles squared over liters squared over on the right-hand side. And the K that you don't know is sitting here in the middle. So what did you do from there?
Well, we needed to isolate the K, so we multiplied liters squared, like on both sides.
Okay, multiply by liters squared on both sides. And that has the effect, whoops, I got that right there. That has the effect of, on the right-hand side, getting rid of liters squared. And so then you've got, on the left-hand side, your liters in the denominator, canceling one of your liters from the liters squared. And so now your liters are gone from the right-hand side, and you've got just liter moles on the left-hand side over seconds, the unknown K that you're trying to get by itself, and then moles squared. And to finish, what's the last step?
Dividing mole squared.
Divide by mole squared to get that K by itself. This is the real miracle of dimensional analysis, that units act just like variables and numbers in an equation. So if we want to get the K by itself, we're going to do the same thing that we would have to do if instead of working with units, we were working with expressions or numbers. If we're multiplying by moles squared, for example, then to fix that, we'll have to divide by moles squared. And so on the left-hand side, we end up with units that are liter moles divided by seconds times moles squared. And since we have moles as a factor in the top and bottom of this fraction, we can cancel the one on top with one of them from the bottom and get the answer that this group has gotten, that the units of K are liters per second per mole, if you want to read it like that. So just a couple things going on there, right? We had to, first of all, put in all the units that we knew in the original equation. And we happen to already know what the units of C were just based on what C represents in the problem. We also had to figure out what were the units of the derivative dc dt. That's a step that is underrated. Make sure that that step doesn't get overlooked. To find the units of the derivative, it's the units of C divided by the units of T. Moles per liter divided by seconds. Then just doing the algebra to isolate K, we find out the units that K has to have.